Hey everybody, welcome to topic 2 in our nuclear physics discussion. And here we're going to start to talk about nuclear radiation. We'll focus on alpha and gamma after we talk about this table in this video. In the next video we'll look at beta and gamma again. So this table shows the types of nuclear radiation that an unstable nucleus can emit. And the radiation is something that's going to be flying out of the nucleus, ejected by the nucleus. So you can see we have alpha, two types of beta and gamma. We still use alpha, beta, gamma, even though we now know what these particles all are. Early on, when people were discovering nuclear radiation, they weren't quite sure what this stuff was coming out of the nuclei, so it got tagged alpha, beta, gamma. And we still use those terms, but we now know what the structure of these different types of radiation are. So for instance, alpha radiation, we now know that those are alpha particles. Those are two protons and two neutrons bound together, which is a helium-4 nucleus. And I've mentioned in previous videos that these are going to be large unstable nuclei that are going to be spitting out helium-4 nuclei, alpha particles. There's one exception. There is a very small nucleus, beryllium-8, which is extremely unstable. And what it does is it just splits into two alpha particles. But that's an exception. All other alpha emitters are going to be large nuclei. Then there are two types of beta decay. There's the beta minus, which we now know is an electron. So certain unstable nuclei will spit out an electron from the nucleus. I know it's very strange, right? Because we normally don't think of electrons inside a nucleus. We'll discuss that in the next video. But you also can have some unstable nuclei that will spit out a positron, which is the anti-electron, the antimatter electron. So that's known as beta plus decay. And then gamma rays are high-frequency photons. But gamma rays are always going to follow either alpha decay or beta decay. So gamma radiation is going to follow alpha or beta decays, which is why we're going to talk about alpha and gamma in this video, and then in the next one we'll talk about beta and gamma together, because an alpha or beta has to occur first before a gamma ray photon can be emitted. And we'll see that the gamma ray photon is coming from what we call the daughter nucleus of the alpha or beta decay. All right, but we'll look at that again in more detail. Okay, I don't know if I mentioned that X-rays also can come from nuclei. So a nucleus, when it undergoes a transition, can emit X-rays. I didn't include that in this table because that's not traditional unstable nuclei radiation. Okay, all right. So let's look at alpha decay in more detail. Okay, so again, the process is a relatively large nucleus is going to eject this alpha particle, two protons and neutrons bound together. Now, we are going to learn how to write what we call decay equations for these different decays. And generally, what it's going to look like for alpha decay, you're going to have what we call the parent nucleus. So where it says parent right there, you would put the chemical symbol for the nucleus. Then you would have the atomic number and mass number in the usual place. You'll draw an arrow representing there is a decay, right? Unstable nucleus is decaying into what we would call the daughter nucleus. So where it says daughter, you would put the new chemical symbol. And then it's going to spit out this alpha particle, which we'll write as a helium-4 nucleus. So you see He, the chemical symbol for helium. Downstairs we have 2, the atomic number. Upstairs, the mass number. Now, we have to balance or conserve atomic number, number of protons, and mass number, total number of nucleons. So you're used to balancing equations in chemistry for chemical reactions, so it's similar for these nuclear decays. So because we have 2 protons in the helium nucleus, we're going to have Z minus 2 in the daughter. Z, remember, is the starting atomic number of the parent. And similarly, the mass number of the daughter is going to have to be the parent mass number minus 4, because we have 4 nucleons right here in the helium-4. So that's how we'll balance the equation. Now this would be a no gamma decay. So in this decay, there would be no gamma following this. But it is possible, as we'll see below, that you can get a gamma decay. All right, now, before we get to that though, anytime there is a nuclear decay, there's going to be energy released in the decay. We call that the Q. And the way we find, and when I say energy released, for instance, in this decay right here, this helium nucleus is going to come flying out of the nucleus, right, of the big nucleus, the parent nucleus. It's going to have some kinetic energy. So that's what we would mean by the energy released in the decay. Okay, would be the kinetic energy of this alpha particle. We're assuming the daughter is so massive that it's just sitting there. In reality, the Q is shared between the alpha and the daughter. They both get some kinetic energy. But we'll always say that, well, the daughter's so big that its kinetic energy is very small compared to the helium. Okay, so how do we calculate this Q? Well, we calculate it through another mass deficit calculation. Thank you, Mr. Einstein. It's really cool. What happens is, if you look at the mass of the parent, there's more mass over here on the left side of this decay with the parent than there is mass on the right side of the decay. So if you add up the daughter mass and the helium-4 mass, that is less than the mass of the parent. Some of the matter, some of the mass of the parent gets converted into the Q, the energy released in the decay. So this is a direct mass or matter to energy conversion. So we have to find the mass deficit, multiply by c squared, we have the energy released. So for this alpha decay, to find the mass deficit, we take mass of the parent, and this will be the atom since we're using atomic masses in that table, minus mass of the daughter atom, minus mass of the helium-4 atom. We'll do an example in a little bit. Okay, now here's where we have gamma decay following alpha decay. So what happens is, the way you'll write this is, you'll write it just like you have up here with the alpha decay. You see that right there? You have parent going to daughter plus helium-4. But what happens is that the daughter is left in an excited nuclear state. So again, the nucleus has energy levels just like an atom does. So in this decay, the daughter is in a higher energy state, nuclear state. We indicate that in the decay equation with this asterisk. You see that little asterisk? What happens then is the daughter nucleus makes a transition to a lower energy state. And in the process, a high frequency photon, that is a gamma ray photon, is emitted. So the gamma ray is really coming from the excited daughter. So right below this equation, we would just write the excited daughter, we have a little asterisk, going to the unexcited daughter, no asterisk, plus gamma. Okay, so that would we would write that right below here. Okay, and I'll emphasize that the gamma ray is coming from the daughter, not from the parent, but we wouldn't have the daughter if we didn't start with the initial alpha decay of the parent. Okay, all right, let's do an example. So we're going to first write the alpha and gamma decay equations for radium-226, and then we're going to find the total energy released in the decay, the Q of the decay, and then we'll do something else because we have some more information about the gamma ray, and you'll see that in just a minute. Okay, first of all, let me go to that isotope table. I want to show you guys, if I look up radium-226, so let me end this, and let me go to that table. I have to scroll down here, right here, isotope data, and let me make this bigger so you guys can see it. Okay, now, whoops, that's good. Now I have to find radium, right? Now I could search on this table. I know it's a big guy, I mean, you could also Google it real quick if you wanted to. So I'm just typing in radium, and I see right here, it's atomic number 88. So that'll help me. I'm looking now, I have to go down to 88, and there it is right, nope, there it is right there. There's radium. Now I'm interested in the isotope radium-226, so this table does have it. Again, this table doesn't list every possible isotope of every element, but I do see radium-226. And if you come over here in this column, you see how, I hope you can see in the video, it might be fuzzy, but there's an alpha, comma, gamma. If it's fuzzy, call this up on your computer, go to our course page and call it up, and you should see it, alpha, gamma. So this is telling you, in this column, if you see alpha, beta, or gamma, right, that's telling you that this is an unstable nucleus, and this is the type of nuclear decay it undergoes. So we see that radium-226 undergoes alpha and then gamma. If you see just a number with no alpha, beta, gamma, oh, there's actually another type of decay. It's called electron capture. So you might see EC. I'll talk about electron capture in a subsequent video. It's an alternative process to beta plus decay. It's not real common. I don't know. I'm looking. Do you see any? You might see some of these lighter guys. Oh yeah, see right here, EC. That's electron capture. So that's also means an unstable nucleus. Again, it's not real common, and we'll talk about it when we talk about the beta decay. But if you don't see any of those letters, alpha, beta, gamma, or EC, and you just see a number, that means the nucleus is stable. It is not radioactive. And the number tells you the approximate percent of natural abundance. So for instance, let's look at lead. That has a lot of stable isotopes. See lead right here? All right, so look, you see lead 206, 24.1. You don't see any alpha, beta, gamma, right, or EC. So this is not radioactive. It is a stable nucleus, and if you go out and dig up some lead, roughly 24% of it will be lead 206. About 52% will be the stable isotope lead 208. Okay? So, and now there are unstable isotopes of lead, like you see right here, lead 204, it's a beta minus decayer. Now they did actually also include a number there, that's the percent natural abundance, but that's just special for that isotope. They decided to list the percent natural abundance for that, about 1.5%. Okay? All right, so sometimes I'll ask you on a test, or, you know, like, hey, is the daughter of this decay stable or unstable? So you can just go to this table and look up. If you don't see alpha, beta, gamma, or EC, right, you know it's going to be stable. All right, let's go back to our problem. So what we're going to do first is we're going to write down the alpha gamma decay equations for radium-226. Okay, so what I do is I start with the parent, Ra, right? I know that's 88 protons, and I know the mass number is 226. I then write over here my helium-4, right? That's my alpha particle. And then I just have to conserve, right, balance my atomic number and mass number. So if this is 88 and this is 2, I know that the atomic number of the daughter is 86. I also know that the mass number is going to be 226 minus 4. That's going to be 222. So I need the chemical symbol for atomic number 86. So what I can do is I can go to my table. I look up 86. That is radon. Radon. Okay? And I know that the isotope, right, is 222. Oh, look, I got lucky. That's the only isotope for radon listed in this table. That's the one we want, radon 222. Okay? Oh, and by the way, look. It is also going to be radioactive. All right, so interesting. That's not a stable daughter. But, okay, radon 222. That's the information that I needed. So I can go ahead and put in radon 222. Now, because the radium 226 is an alpha gamma emitter, I know that this daughter from the alpha is going to be in an excited state. So I put a little asterisk here. It will then emit the gamma, so I just write excited daughter going to unexcited daughter plus gamma. All right? I mean, I put the atomic number and the mass number there for completeness, but they're not going to change. Okay, so again, the radium we call the alpha gamma emitter, but really it's the daughter of the alpha decay that spits out the gamma. Okay? And then we found out by looking at the table that this daughter right here, this unexcited radon-222, is itself radioactive. Okay, so we could write down the decay equations for that, the alpha and gamma decay equations for that if we were asked to. But we'll stop right there. Okay, so we got the decay equations. Now we're going to find the total energy released in the decay, the Q. So the recipe, remember, is we find the mass deficit for the alpha decay. We take mass of parent minus mass of daughter minus mass of helium-4. So I go to that table. Oh, let me show you. Sorry for all the clicking, but I just want to show you. I'm going to my table, and I need the mass of radium-226. There it is right there, 226.025406. I need the mass of radon-222. I got it right there, 222.017574. And then for alpha decay, I'm always going to need the mass of helium-4, which is right here, 4.002603. A lot of numbers, but all those digits are important. All right, don't round too much because sometimes these differences in mass are very small. So you can see that's what I'm doing right here. I'm just putting in those masses. I subtract and I'm left with 0.005229U. So then what I do is I multiply by C squared to get Q, but I'm going to use once again this handy dandy conversion factor. 1U is 931.5 MeV per C squared. So the C squareds cancel, the U's cancel, and I'm left with 4.8708 mega electron volts. Okay, now that energy is going to be shared with the alpha particle and the gamma ray. Again, we'll assume that the daughter is so massive that we'll say, yeah, it doesn't really move that much. So it's really just going to be kinetic energy of the helium in the gamma ray. Okay, but look, we're given more information. We are told that the gamma ray from this decay has a wavelength of 0.0067 nanometers. Okay, so these gamma rays, depending on the decay, they are going to have certain wavelengths. Okay, and now sometimes there might be two possible wavelengths. One has a greater probability of occurring. So in the initial alpha decay, the state that the daughter is left in, it might be more than one possible state. So there'll be, probability that you'll get this gamma ray versus this gamma ray energy. All right, but here we're told that the gamma ray has a wavelength of 0.0067 nanometers. How much kinetic energy is then left for the alpha particle? Okay, so what we can do is, since the gamma ray is just a photon, we can find the energy of that photon. Remember, we know how to do that, right? It's hc over lambda, or 1243 eV nanometer over wavelength, right? That's how we find the energy of a photon. So I'm going to stick in the wavelength of the gamma ray. I'm going to make sure I have it in nanometers. I do. All right, and when I do that calculation, I'm left with 185,522 eV. Now, we'd like to work in mega electron volts for this nuclear stuff, so I'll convert that, divide by a million, right? And I've got 0.1855 MeV. Okay, so then what I do is, this is the total energy released. If I just subtract the photon energy, whatever's left over should be the kinetic energy of the helium-4. There it is right there. So in this decay, the helium-4 is going to be flying out with 4.6853 mega electron volts. Okay? So you should know how to do a calculation like this. Okay? So, know how to write the decay equations, and if there's a gamma decay, realize that you may have to find the photon energy, right? And then if you subtract that from the total Q, you can get the kinetic energy of the alpha particle. So that means also know how to find the total Q, the total energy released, by doing this mass deficit calculation. Okay, I'll see you in the next video. Bye-bye.